Hello, everyone. My name is Francesco Ballarin from Università Cattolica del Sacro Cuore in Brescia, Italy. And it's my pleasure to welcome you to this first seminar of the numerical analysis of Reg-ROM seminar series that we organize together with Maria Strazzullo, Virgul Koch, and Traian Iliescu. You probably have already browsed our website, but just as a reminder, the main purpose of this series is to serve as a forum for the, say, Galerkin or Petrov-Galerkin community, reduced order modeling community, to exchange views on the achievements, but also on the open problems. And with this span that we also inserted in the logo, we've called them the nagging open problems in the numerical analysis of Galerkin ROMs, based, for instance, on proper orthogonal decomposition or reduced basis methods or related techniques. So the goal of this series is to be a forum for an exchange of ideas among the members of this Galerkin ROM community, and especially those of us who are interested in the development of mathematical foundations of these techniques. The series overall aims at leveraging new mathematical results to develop the next generation of Galerkin ROMs at a mathematical level, for sure, but also for industrial, geophysical, or biomedical applications. It is a pleasure to see so many of you connected to this first seminar, and this first seminar will be given by one of the organizers, Professor Traian Iliescu, and in his talk, which is entitled Regularized Reduced Order Models for Turbulent Flows, he will discuss about his past and ongoing research topics, and at some point he will also have some questions or open topics, so that this seminar, and it would be our goal also for the remaining seminars in the series, so that these talks could be accessible to well-established researchers in the field, but also to possibly newcomers, such as students and postdoc. So with this, I give the floor to our first speaker, Professor Traian Iliescu.
Thank you, Francesco. Can you hear me? Yes?
Yes.
All right, perfect, great. Thank you, Francesco. Thank you so much. It's a great pleasure, really a great pleasure to be giving a talk in the Reg-ROMs seminar. This is the part where I usually thank the organizers, and I know that I'm one of the organizers, but I can still do that. I would like to thank Francesco for his leadership and immense amount of work that he put into organizing this. I think it's a good thing. I really like it. And to Maria, and who's worked so much as well, and Virgil, who's helped quite a bit, right? So thank you all for this, and hopefully this is gonna be something good for us all. Now today I will be talking about Reg-ROMs, regularized reduced order models for turbulent flows. My talk is basically covering a work we've done in our group and with my collaborators, some of which are around here, over the past 5 years or so. It is more about the why. So it's more philosophical, about principles and concepts, and not so much about the what. Of course, I'm selling models and computational models, so I will talk about that as well. But the important thing is to understand why we're doing what we're doing. And I will talk about numerical analysis in so much as it pertains to regularized models, which is not a lot. In fact, I'm aware of only one paper, so we wrote this in our group. But I think that there is a lot of there are lots of opportunities here. The same thing for closure modeling. We also wrote, I believe, the first paper, but there are quite a few others, but not enough compared to what's happening in the classical numerical methods community, let's say. So my focus is on numerical analysis for regularized ROMs, Reg-ROMs. I will talk, as if I can, about related issues, but this is the focus of the talk. All right, so I know I have I know I have 55 slides. Don't worry, I'll breeze through those. Most of them are just pictures and thoughts. Now, so this is the structure of my talk. I will talk about ROMs for turbulence. I will explain why I think it's important to use Galerkin ROMs for turbulence, and very briefly about ROM closures. This is something that we've been developing in our group, but that's not the focus of this talk. I will focus on Reg-ROMs, regularized ROMs, and especially on spatial filters. All right. If I have time, I'll talk a little bit about the length scale, and then at the end, I'll present some results that are relevant to what we've done to the computational models developed in our group. Okay, and I'll end up with some conclusions. Please interrupt me. You can, as far as I know, so Francesco told me that you can unmute yourself and ask questions. You do not have to wait until the end. At the end, I'll try to finish early by my standards and have some time for questions. I would be delighted to answer questions, and we'll take it from there. All right. This is a list of collaborators. So students and postdocs in my group. So it's Ian Moore. So he's working right now. We have a collaboration with Francesco and Anna Sanfilippo. So that's Francesco's student. Dave Wells, Zhuang Shuping, Cheng Hong. So he's a postdoc now. So he's done quite a bit of work for the turbulent channel flow, and Jamon. And collaborators, my co-organizer Maria Satsulo and Professor Canuto, and Francesco with Anna. So they're here visiting us, part of the ARIA project. Michael Schneier and Max, Gianluigi's group, Michele and Anna, and Hong Hu, my colleague here at Virginia Tech. So these are just a few. Most of them are responsible for what I will present next. And if there's some others, I will mention them along the way. So I'm interested, I'm going to try to move this to the right. Okay, so I'm interested in structurally dominated turbulent flows. So here we have two examples. So the first one is a flow past a wind farm. So these are windmills, and you can see the complex turbulent flow behind those windmills, wind turbines. And then to the right, we have a geophysical flow. So we have the flow past the Canary Islands, I believe, in the Atlantic, and you can see the structures in the flow past those islands. You see the von Karman vortex stream. What I want to emphasize is that these are extremely complex phenomena. They're very hard to simulate, but they do display structure, and I think that's where ROM can contribute. And just to make sure we are on the same page, it's very hard to describe turbulence, but so like two of the main features are that it's chaotic. It's a chaotic phenomenon, and as such is very hard to predict. So it's chaotic, and it's multi-scale. So it is not just one scale or two scales or things like that. It's just the billions, gazillions of scales that interact mainly through nonlinear interactions. That's turbulence, a very complex type of phenomenon. Okay, now we're working on convection-dominated flows. So in particular, everything I'm going to show you is going to be for the incompressible Navier-Stokes equations that have both diffusion, a little bit of diffusion, and convection. So it's not just convection, it's not just transport. In other words, I'm not looking at a hump that travels from left to right and then try to simulate that. That's hard for ROMs, I agree, but that's not what we're doing. That's not turbulence. Turbulence is multi-scale, nonlinear, chaotic interactions. Okay. So I know this is not the right, maybe that's not the right place, but just to make sure we're on the same page. So what is Galerkin ROM? So for me, I start with the generic PDE, time dependent. I collect data, right? So this data can come from the full order model computations, think finite element to finite volumes, large number of degrees of freedom. So let's say millions or billions actually, and hundreds of billions. All right, or experiments. And then from these snapshots, we build the basis. And I want so Francesco mentioned this, I'm gonna focus on POD. RBM is something, reduced basis methods is something that Francesco's group, John Luigi's group, so they've been working on for a while, Masta as well. And I think that what I'm saying applies equally well to that. So these are the type of methods, POD, RBM, the type of Galerkin ROMs I'm thinking about. So from the data, we get a very low dimensional basis, and we use a Galerkin or Petrov-Galerkin, so Petrov-Galerkin as well, procedure. At the end, we get the dynamical system is beautiful, low dimensional, perfect. All right. Now, we also have this offline online two-stage process in which in the offline stage, we generate the snapshots and construct the ROM basis and the ROM operators. That's expensive usually. And then in the online stage, we run the cheap reduced order model. A dot is equal to a function of A. Very simple, beautiful. All right. And I wrote this here for the incompressible Navier-Stokes. Okay. All right. So everyone knows this. I mean, this is not the right crowd. I just want to make sure we're on the same page. But a question, this could be a little bit, arguable. But so a question I always get is, why are you using Galerkin ROMs? Why aren't you using like different other things? Yeah, I mean, so like there's so many ROMs out there, machine learning, systems theoretic. There's so many ROMs. I mean, it's like, inference and okay. So, I mean, one could use that, but I want to re-emphasize. So I'm interested in turbulence. I'm really interested in how far we can take reduced order models for the numerical simulation of turbulent flows. So I think that some of these other techniques might have difficulties there. The other argument is that believe it or not, I'm a computational mathematician. I'm still a mathematician, so I like to prove things about the models that we develop. And if you do machine learning, for example, it's gonna be a little bit harder to prove things, basic things. I'm not talking about subordinate spaces and whatnot. I'm talking about convergence, rate of convergence, stability. I want to prove that my model is stable, and scalings. These are practical issues that mathematicians prove for finite elements, right? So can we prove something like that? Again, if you're using machine learning, that's a little bit of a problem, okay? So this was my sales pitch. Now, so let me tell you a little bit about what the issue is when using ROMs, Galerkin ROMs, not any other ROMs, okay, for fluid flows, for turbulent flows. So if you start with here we have a 2D flow past the cylinder. This is the workhorse in our community, in our community. Everybody shows these results for this, including myself. Okay. Here we have quasi-geostrophic equations, and here we have the turbulent channel flow. Reynolds tau 395, so about 14,000 in terms of the Reynolds number based on the bulk velocity. And we can see is that when we plot the decay of the singular values of the eigenvalues, we see that for the 2D flow past the cylinder, the decay is very abrupt. So what this says, that's the amount of energy in the system. So what this says is that with few modes, you can simulate the 2D flow past the cylinder, no problem, and we do. However, if you look at this chaotic system, the 2D quasi-geostrophic equations, or the turbulent channel flow, you see that the decay is much slower, which means that you need more and more basis functions in order to be able to simulate the system accurately. Okay, all right. So here are results that Chang Hong got in his PhD thesis. Once again, Reynolds tau is 395. This is a hard problem for ROMs. All right, and I want to show you why this is hard. So here's why. if you use, and we've done that, if you use a Galerkin ROM with R is equal to 100, the solution will be very inaccurate. So this is what you get with a 100-dimensional Galerkin ROM. Now, the LES results, those were the snapshots, are completely different. There's a major difference between the two. So this shows that Galerkin ROM doesn't quite work. And you can see that as you increase the dimension, 50, 60, 70, 80, so if you think about convergence, for example, you can see that the energy gets better and better. Well, this is the correct energy, LES energy, and this is where you are. That's where we are with our Galerkin ROM. So it's gonna take a lot of basis functions to get there. Even worse for the second order statistics, right here. So you see, we have convergence, 50, 60, and so on. But it's gonna take a while until we get to the LES benchmark values. It's difficult. So what can we do? Now, so we are in the under-resolved regime. Usually you truncate, that's what we do to keep the ROM cheap. We truncate, we are in the under-resolved regime. We have the nonlinear interactions. What's happening is that different wave numbers interact, and they are inaccurate nonlinear interactions, and they are inaccurately represented on two, with the modes that you have in your ROM, the few modes that you have in your ROM. That's why you get inaccuracy when the flow is convection dominated. Think Hyrion's number flows. That's what we want. Then this inaccuracy propagate in the system and become worse and worse. So this is the etiology. Yeah? Okay. Now, what do we do about this? So that they're basically like in classical CFD. So so two types of approaches would be closures and stabilizations. People, sometimes think that the two are the same, but they're not. So there's subtle differences. So although it's easy to mistake them one for another. So closures, they target causes. So they're looking at why you have this inaccuracy, and then they try to fix that problem. Stabilizations, like regularized ROMs, Reg-ROMs, are different. They target symptoms. They say, oh, I don't know why this happens, but we have these oscillations. And then what we want to do is actually decrease, damp these oscillations. Very simple, very practical, so quite different. Yeah. Now, in general, stabilizations are easier, more intuitive, whereas closures are a little bit more complicated. I will very briefly, I don't have a whole lot of time, very briefly say just I have a couple of slides on closures. I don't want to talk about this really, but basically the idea is that here's a schematic that we included in our tutorial, ROM closure tutorial. That's a Springer volume that just appeared. So let's say that you have three modes, your ROM has three modes, A1, A2, and 3, right here, black curve. And then let's say that you want to reduce your reducer of the model has 2. I mean, it's just a toy problem, right? Okay. So the best you can do is to take the black curve and project it onto the A1, A2 plane. What you do is you get the blue curve. Now, if you look at the blue curve, it's beautiful. Perfect, that's the best you can get. But the problem is that it depends on A1, A2, and A3. So it depends on A3. So then what people do is that they discard this dependency. So for example, you can consider this, you can set A3 is equal to 0, for example. Yeah. Okay, well, this would be practical, just 2 degrees of freedom, A1 and A2. So that's reduced for the modeling. The only problem is that because we ignore the dependency on A3, we're making an error, and that's the closure error. And that's what closure is all about, trying to take this red curve and try to push it down as close as possible to the blue curve. And this is achieved with the green curve by adding these extra terms. So we have some correction terms that depend on A1 and A2, and they just mimic the action of A3 dependency. All right, so this is the very schematic toy problem just to illustrate what closure is. There are different ways of doing this. And one, probably the most popular one, is the physical one, in which you say that the role of these discarded modes is to dissipate energy. This is a paper, Kamami paper from 11 years ago, that uses classical CFD type of approaches And we got good results. Good speed up with 6 modes from 500,000, so 500,000 to 6 modes. And we integrate longer in time. So these were good results. If you're interested in more about closure, I mean, there are many other data-driven models and mathematical models. This is a recent paper, survey paper, Physics of Fluids with Bert Nowak and Son, and we explain the different types of closure models. I don't want to talk about this, so it was just a few slides. Okay, what I want to talk about really is regularized ROMs, and these are obtained, these are stabilizations that are obtained through spatial filtering of the Navier-Stokes equations, either for terms in the Navier-Stokes equations or even for the entire solution. The idea is simple. I really like this. It's intuitive. You have oscillations, you use spatial filtering, you damp those oscillations. Simple. Beautiful. I'm going to talk about 2 models, the Reg-ROM and the Voltfilter Relax. And there's several other type of models that we're working on, like Francesco and Maria and Ping-Xuan and Paul Fisher. So we're working on different types of Reg-ROMs. Yeah. But these are the 2 that I'm going to present today. Very simple. I mean, really simple. And I hope that, so if you're a young person looking at something to do, you're dying, let me do something. This is one thing that really simple models. So you take the Navier-Stokes equations. I wrote the ROM for the Navier-Stokes equations. I wrote them here. And then you just filter the convective term. So the U in U dot grad U, you filter the U. Right? What this means at the matrix level is that you have a B bar, the tensor, so in which you filter the basis functions so that enter in the tensor B. It's very simple. Okay, now simple model. I like it. This was derived by a mathematician in 1934. See, vision, right? So this was for different computers at that time, so for different purposes, to prove existence and uniqueness of Navier-Stokes of weak solutions. But then recently it's been applied, 20 years ago, it's been applied for classical CFD by Holm and Gertz and all. Now, it is related to the Navier-Stokes alpha. If you use the differential filter, I'll talk about that, that Foyage, Titi, Daryl Holm developed 2 decades ago. Okay. Now, it's been used at the ROM level for, 1D, Kuromoto Sivashinsky, Navier-Stokes, Boussinesq. So here work by Ping-Xuan and Paul and Kento, quasi-geostrophic equations, Michele, Annalisa, and Gianluigi. So quite, different types of equations. Okay. Now, the second model that I'm going to talk about is the Evolve Filter Relax ROM. That's even simpler, I think. So it's just very, very intuitive. So basically what you do is this. You have your solution, ROM solution in the current time step, and then you evolve for 1 step with the current code, the Galerki ROM code. Then in second step, you filter this intermediate solution. And in the third step, you relax it. So you take a linear combination, like convex combination of the 2, the filtered and the unfiltered intermediate velocity. That's what you call the velocity at the next step. Very simple. We've done this, recently in these 2 papers, but this is something that has been used for ages in the spectral methods community. Yeah. So here's a classic textbook. Yeah. Spectral element methods. I learned it from Paul Fisher. And also in the ROM community, so this has been extended. We've been extending this to the ROM. It's an easy type of extension. Okay, so far I've talked quite a bit about I've talked about the Reg-ROM and the EFR ROM. One thing I didn't tell you is what filter I'm using. So for FOAM, for classical CFD, there are many types of filters: Gaussian, box, sharp cutoff, differential. Oh my gosh, so like many filters. How about the ROM? So the simplest filter is the equivalent, the analog of projection. So basically, you represent your function in the ROM space with a lot of basis functions, and then you take that and you chop off the components starting with R+1. So that's the projection. That's the L2 projection of your signal. Very simple. And of course, since the first basis functions usually capture the larger scales, this has the role of a spatial filter. Yeah, very simple. All right. So so this, so spectral element people, they always use this. I learned this from Paul like 20 years ago, and we've used this in the ROM community. So actually for closure model first, then for regularized ROMs, and Paul and Kento and Ping Xuan, they've been using these for complex problems as well. It's a good, very easy filter. All right. The next one is a little bit more complicated, right? But this one is a differential filter. So basically what you're doing here is that you take your ROM velocity and then you solve this elliptic equation. So you solve at the matrix level, mass matrix. So then you have the stiffness matrix scaled by delta squared. You solve this system of equations, low dimensional. This gives you the filter velocity with the differential filter. And we've done this at the ROM level. Of course, this was used, the differential filter for fluids by Germano and all, 4 decades ago. I want to emphasize that we can use high order filters. And these are two variants. And we've looked at those. They're much easier to use at the form level. At the form level, you have to solve a huge system of equations. This at the ROM level, it's an R by R system of equations. Very easy. All right. Okay. So does this work? All right. Well, so here's a paper IJNME from 5 years ago, 2017, Nate Wells and all. So here's what we have. We have the DNS flow past the cylinder, Reynolds equals 1000. And GROM produces inaccurate results. You can see this here. Loss of structure that is just spurious. These are spurious structures. Okay. In the middle row, we have the Reg-ROM. First with the projection filter, then with the differential filter. In the last row, we have EF equal filter with projection left and differential filter right. And you can see, actually, overall, the best results are obtained with evolve filter, with the differential filter. But then the LROM, the Reg-ROM, with the differential filter works equally well. So in our numerical experiments, it looks like the differential filter does make a difference. So it is a good filter. I wouldn't be able to say which one works best. I would say EF, right? But the differential filter is very important, because if you use the projection filter, you get bad results. Okay, now these are more recent results on the turbulent channel flow. And here we have, so this is a recent paper on the archive. So here we have the benchmark LES. I've shown you this picture, and I've shown you this picture as well. And this is the Galerkin ROM that is 100 dimensional. Again, these are bad results, inaccurate results. And look here, we have EFR, evolve filter relax, with R is equal to 8. Which one looks more similar to the LES? I think the results are clear. Yeah? So 100, 8. But these 8 are with, so this is for regularized ROM. So with spatial filtering. You see the effect? The effect is significant. And you can see this for statistics. So here we plotted kinetic energy, the time evolution. Now, R equals 8, EFR is not great, but it still does the right thing. Whereas the purple one, so the maroon one, just grows. So the Galerkin ROM with R equals 100. So R equals 100, R equals 8. And you can see this when you look at the second order statistics. The Galerkin ROM is way off, it's really inaccurate. Now, EFR ROM is much better, but is it accurate? So is relatively accurate. Ping Xuan and Paul asked questions about this, but it's not within 10% accuracy. So that's something we did not get. Yeah, so for that, you need to increase the size and play a little bit if possible. Okay, so these are the things that I wanted to present about the regularized ROMs. There have been quite a few developments. So with my colleague Hong Hu, and then with Mike Schneier and Max, my academic grandfather, we looked at the stochastic version of these regularized ROMs. So the impact they have in stochastic PDEs. With Maria, Francesco, Michele, and Gianluigi. So Maria led this effort on model consistency. In other words, do you have to filter only at the ROM level or only at the FOM level? And our conclusions were that it's good to filter both levels. So even if you filter at the FOM level, that's not going to be enough. You still can get inaccuracies. I think that's important. So the two things that I was planning to talk about is ROM length scale, and I will be very brief, and then spend the rest of my talk on numerical analysis. Are there any questions at this point? Anything that I could clarify? I don't know. You can unmute yourself and ask.
Hi, Traian. I have a quick question. 100 is the rank of your snapshots metrics, or
no?
What is 100?
No, so it's just the dimension of the ROM. That's a great question.
Yeah,
so
but it's the rank, or
it's not the rank. It's not the rank. The rank
okay,
is higher.
Thank you.
You're welcome.
Okay.
That's a great question. That's a great question. You're very welcome. In fact, Ping Xuan, so he's running now, he's in the audience, so you can ask him the tough questions. So Ping Xuan and Paul Fisher, so they're running a thorough investigation of what you need for the G-ROM to simulate the turbulent channel flow. And the situation, we should have a paper soon, and the situation is really difficult. So it's really challenging for Galerkin ROM. This is excellent. Yep. It's an excellent question. Okay, very good.
Thank you.
You're welcome. Any other questions?
I have another question.
Yes.
Thank you for this first part of the talk. You showed result with LES.
Yes.
And for the Galerkin projection, the different type of reduced order model, you project on Navier-Stokes or you project on LES?
Excellent question. So I didn't get I cannot see somehow. I cannot see who's talking. So who's the question from? Can you? Oh, so then Valentin. Okay, nice to meet you. Nice to meet you. It's an excellent question. That's an excellent question. So the answer is no, and I know where you're going with this. So basically, we used an inconsistent type of formulation. So we used the LES. An LES formulation which is also a regularized formulation, but is different from what we used at the ROM level. So these two are not the same. And you're right, we project it on the Navier-Stokes, not on the LES equations. What you said is correct. And I think that what you're alluding to is that, especially in the light of Maria's work, and I think, and Gianluigi's group, they've looked into this quite a bit. I think that actually, probably, my personal opinion is that we should have projected onto the LES type of equations, and probably this would have helped. That's my gut feeling. We haven't done this. The only problem with this is that, you see, from a practical point of view, it's usually very hard to get your hands on what exactly. In this case, we could, but in general, it's hard to get your hands on what people have used to generate the data many times. So then we said, oh, okay, so right, I mean, so, but you're right. I mean, mathematically, it would make perfect sense to me, it's a personal opinion, to be consistent in terms of equations and formulations you're using when you go from FOM to ROM, although it's hard in practice many times.
Okay, thank you.
You're welcome. Excellent, Valentin. Excellent question. All right. Okay. Any other questions? No? Okay. All right, well, we can ask later. So now I'm gonna talk maybe not even 5 minutes about the ROM length scale. I'm very excited about this, but I want to get to the numerical analysis part. So the very quickly, the ROM length scale is a very simple question. So see, I told you, so let's say we're using EFR. I like this model, we like this model, we investigate this. And the spatial filter, and I told you what the spatial filter is. But let's say that we're using the differential filter. Now that one has a length scale, the radius of the filter, delta. What is that? And this is to me, this is a generic question. So we're using ROMs, all of us. And let's say that we're using 10 basis functions, 20. So for a given number of basis functions, an engineer could ask you, what are the length scales that you're resolving? Are they 1 centimeter? Are they 1 meter? Are they 1 kilometer? Yeah, I think this is a good question. And I want to emphasize that if you look at FOMers, so classical numerical methods, this is an easy question to answer. But the finite element level is the mesh size. Same thing for finite differences, finite volumes. For spectral methods, the same thing. You can come up with the wavelength, and right. I mean, so you can tell people based on the number, your resolution, what length scale you're resolving. Can we do this for the ROMs? That's a good question. So there are not so many people looking into this, but here's the problem formulation. So I want to have some form parameters like H, the domain of the computation, the length of the computational domain, and some ROM parameters, the number of basis functions, the ROM dimension, the total number of basis functions, eigenvalues, I'm using POD, and the basis functions. And the output should be very simple, delta, a length scale that in principle we're resolving. So really the first one, and to my knowledge, there are not so many. I mean, so this is one of the few I found, the only one I found really, is the one proposed by Lumley in his pioneering work. And this is based on dimensional arguments, so 1988. So he came up with this dimensionally sound formula involving the fluctuations. Okay? Now, we developed a different, in a recent paper with Omer San, Elia Mezzari, and Chang Hong, a different length scale based on energy balance. So here's our idea, very simple, but okay. So the principle is this: let's call lambda the sum of the eigenvalues using POD that we keep in the system over the total number of eigenvalues. So this is the relative information content. This has many names. But really, what this is the kinetic energy contained in the resolved ROM resolved scales, delta 2, over the kinetic energy that you have in all the snapshots, which should be the kinetic energy in the small, the form length scale, little h, which is given. That's the input. We took this formula. We used, Kolmogorov's statistical theory of turbulence, this type of statistical expressions. We plugged them in, and we got a beautiful result. So we defined delta 2 as capital lambda times h to the 2/3 plus 1 minus lambda times capital L to the 2/3. Everything to the 3/2. So h is the form mesh size, very small, and capital L is the domain of the length of the computational domain, very large. Dimensions match. Lambda is dimensionless, so this is perfect. But asymptotically, when you increase the number of basis functions, lambda goes to 1. This term disappears. 1 minus lambda is 0. So then you basically have h to the 2/3 to the 3/2. So that's just h. Delta, our length scale, goes to h. It makes sense. If you take all the snapshots, if you increase the maximum, the ROM dimension to the maximum, you should resolve the smallest scale. On the other hand, if you go in the other direction, if you just take one length scale, one ROM basis function, lambda becomes 0, almost 0. And then what you're left with is capital L. So you're resolving only the largest scales, which are the computational, the size of the computational domain. So this makes sense asymptotically. We've done this, we've investigated this in the turbulent channel flow, and voila. So first of all, this delta 1 is Lumley's dimensional length scale. Delta 2 is our length scale for different R values. And you can see that as we increase R, Lumley's dimensional length scale pretty much stays the same. We increase R, our length scale changes, becomes smaller and smaller, which is consistent with this correct asymptotic behavior. Okay, now, so this is really what I wanted to say now, a few minutes. Oh man, so I'm gonna spend maybe I don't know, 10 minutes or less, hopefully, on the numerical analysis. And I'm gonna talk about two main results. So the first one, since I'm using regularized ROMs, for us, we've asked from day one, what can we prove about the differential filter? Okay, now there are theorems and there are results at the finite element level and classical, numerical analysis level, but not at the ROM level. And we tried to mimic those results, I'll be honest. And the best we could do was to get a bound of this form. It's an ugly bound because it involves parameters coming from different sources. So it involves parameters like form parameters, length scale, mesh size H, and delta T, time step size, but also ROM parameters. So we have some of lambdas here and some of the one semi-norm, actually phi j squared lambda j. So you have a combination on the right-hand side, a combination of form parameters, finite element parameters, and ROM parameters. Okay. Now, what we did was we investigated this numerically. So we proved this bound, and then we investigated this numerically. In other words, do we recover these scalings in our numerical experiments? Again, finite element parameters and ROM parameters. So we looked at the L2 and H1 errors and the scalings, the theoretical scalings with respect to delta, for example, and lambda H1, which is this ROM quantity. And we've shown numerically that these scalings are obeyed. So this is a paper from 2018. And what I mean by this, I want to make sure that we're on the same page. We did exactly the same thing that finite element people do. I'm a finite element person. I came out, but I'm telling you the truth. And that's what people do, finite element people do. They want to see that as you decrease delta, for example, you get the scaling that you're supposed to get, and you get that. Similarly, as you decrease this lambda H1, you get the scaling that predicted by the theory. And you can see that these scalings are indeed recovered. Now, I want to say that actually, so here's, I said at the beginning of the talk that I'm gonna show you the good, but the bad and the ugly as well. So the bad news. You see, so we recovered all the scalings, except that at the H1 level, we got superconvergence. Now, usually this is a good thing, right? I mean, so you get the extra stuff, but it could also mean that maybe your bound is not super sharp. And in fact, I believe that we can sharpen the bound and we can get better scalings with respect to delta, the length scale of the filter. And the finite element people did get better scalings for the finite element discretization. But to do so, they use the result on the H1 stability of the L2 projection. That's all result proven by Bank and some others, like 4 decades ago, in finite element for finite elements. we could improve it for ROMs. So this tells me that, yeah, I mean, so we did prove these bounds, but maybe one of them is not sharp. And the numerical results kind of suggest that. This is an open problem. If we could prove that H1 stability of the L2 projection, then I believe we can prove better scalings. That's something for the young and energetic people to do. We're young at heart. And I think it's very interesting. Fundamental result for finite elements. For ROMs, but you see, has a practical implication, I think. Okay, now we use the error. Let me see how much time. Okay, 10:47. So we use this filtering error bound, and we plugged it in, and we got an error bound for the Reg-ROM solution. So this is the paper. I was the same paper, and we got an even uglier bound, obviously, for the error of Reg-ROM. Okay. Again, it's a combination of parameters. It has parameters coming from finite element, and it has parameters coming from reduced order modeling. Okay. And we investigated those again with respect to delta, with respect to the time step, and with respect to lambda H1, which is this quantity. Everything panned out. But again, with respect to delta, it looks, so we got superconvergence, which again suggests that there is something there. There is more, that one can do more about that. Okay, so this is theoretical, and I would love to discuss with you the if I remember right. So you can find more details in the paper, but this shows you that numerical analysis has a place. It's not just we prove estimates and the better bounds and then we leave it at that, but it also has a practical effect. So one could use, like in finite element, for example, one could use these bounds to find scalings for regularized ROMs, stabilizations, closures, what have you. Otherwise, the only thing I can do is use machine learning or data-driven model, which is an option. I'm doing that as well. So yeah, just wanted to be, I think, but this is mathematical. Yeah. So there's a chance to have robust scalings. That would be great. Like finite element people do. There are textbooks on this. Those guys are set. Okay. Now, this is another. I have a couple of slides on SVPG ROM. But this is something that my friend and collaborator Volker John has worked on quite a bit, and Julia Novo. So she's worked on this as well, and they're gonna give talks about this. I don't want to talk too much about this. I just want to say that, and this is not a regularized ROM. As SVPG ROM is just a so it's a stabilization, but so SVPG ROM is based on residual. It's a residual based stabilization, right? It's not filter based. Okay, so but I think it's relevant, the spirit of it. And so with Volker and his students Sveta and my former student Dave Wells, we look at finding the optimal theoretical parameter in SVPG ROM. Okay, so what is delta R in SVPG ROM? And basically, we ran across the following problem, and I think Volker and maybe Julia will talk about this. So basically, you can use inverse estimates at the finite element level, classical, or use those derived by Stefan Volklein and Karl Kunisch 2 decades ago at the ROM level. They're both valid because the ROM space is a subspace of the finite element space in our implementation, right? Which one do we use? Well, it turns out that if you use one, you get the classical scaling, the finite element scaling. If you use the ROM inverse estimate, you get a different scaling. Both valid. Which one is better? So we ran this on a test problem, and it turned out actually the finite element was doing a little bit better. For lower number of modes, I still think that there is room for improvement for the ROM, but it was interesting to see that we have different scalings and both are good, both are improving the results, but one is better than the other. That's an important question. Can we use math to decide which one to take out of these two choices, for example, because both are valid mathematically. Maybe we should use a different criteria. Okay, the last slide I have is not on regularized ROMs and is not on stabilized ROMs. It's on one of our most recent pieces of work, closure. I've devoted a lot of time in our group. We devoted a lot of time to closure ROMs. And this is a paper with you and Chang Hong Hu, my colleague, Zhu, and Gianluigi. And this just appeared, well, late last year, and it's called verifiability. So the closure model is a data-driven closure model, data-driven variation multiscale. We use data to build the closure, these correction terms. And what we can prove is that the error in the closure drives the error in your ROM. So in other words, if we make the ROM, the closure model smaller and smaller with data, so better, lower and lower, then we can decrease the error at a ROM level. We could prove that. And what allowed us to prove it was that we were in a Galerkin framework. I really don't know how to do that without a Galerkin framework. And it's an important result. If you put more data, you want to prove to be sure that your model gets better. It's a simple thing, right? It's intuitive. I mean, it's natural. But I don't know if other models, if you use machine learning, can you do that? Maybe, maybe not. Yeah, I don't know. Okay. And the other thing was that, yes, data, how do we make it smaller? By using more data, better data, and so on. Right? This is called verifiability. This is done for classical CFD. There are results for finite element, let's say, but there are no results for ROMs, as far as I know. And I think that's an important question, mathematical question, numerical analysis question. Okay, so I will wrap it up. I started at 10:05, so 15 minutes. I think I'm good. So turbulent flows, I think that usually they happen in the under-resolved regime, and they usually yield oscillations. People who've worked with turbulent channel flow and turbulent flows, they know that. Yeah. Okay. To me, they're just like in classical CFD, two main ways of doing that. And I will include, I mean, I would say Petrov-Galerkin methods are pretty much like SUPG. SUPG ROM is a Petrov-Galerkin method, right? So stabilizations, I think that's the easiest way. You look at the symptoms. Closures are effective for turbulent flows, but they're more complicated and they require more work. I really like Reg-ROMs. I think they're easy, simple. Anybody, you have a ROM code, you can implement this in an afternoon, not even. Now, I'm not saying testing it and finding optimal parameters, just implement it. Very easy. Simple, modular, just one subroutine you add to your code, and effective. They do the trick. I talked about filters. I think projection is a good filter. It's very simple, intuitive, but I like these differential filters. And the length scale, I think I really like the energy-based length scale that we've come up with. We don't have any mathematical theory. That's something that one could think about. Okay, numerical analysis. In this group, maybe in this crowd, it's easy to justify it. We're mathematicians, we love numerical analysis, but I think engineers will always ask you, why do you care? They asked me. It was an embarrassing moment. So, I mean, one classical answer, for example, in finite element, one classical answer is scalings. It would be great to get scalings for these many parameters that you see in all the data-driven models. That would be great, right? The other thing is a little bit more subtle. So like convergence. This is something that maybe John Singler or Bill Gill will talk about, the difference quotients and how this has an impact on we have a recent sign-on paper, which is talking quite a bit about pointwise estimates. I think these are new. So, but why do we need convergence? This is something that has stuck with me. Do you need convergence if your reduced order or your ROM is 10-dimensional? If you have 10 degrees of freedom, the dimension is 10. why do you need to see what happens when R goes to infinity or something like that? I mean, in my opinion, that's what an engineer would ask. They ask this question. So I think that the answer is we probably don't need that, very honestly. But I think that if you look at turbulent flows and in general, systems that require lots of modes, you see in these turbulent flows, they require hundreds, we're gonna get to the thousands. And people are doing that in atmospheric flows. And tens of thousands. So in those cases, we do need that. I really think that we need to know what happens when you increase the dimension. Do you really get some sort of convergence or not? I think it would be nice to be able to prove, even in the simplest settings, like people doing finite element, right? I mean, we still don't know that the Navier-Stokes equations have a unique solution in 3D, right? But we can prove error estimates in 2D for laminar flows, and you know, use that insight to move on to more complicated problems. So my vision, how ROMs for fluids look at the end of this decade, Reg-ROMs, I think, will be, you know, practical, maybe mathematically supported component. So numerical analysis of Reg-ROMs, NAG-ROMs. All right. This is a list of papers. They document what I've shown you, so quite a few people. And I will end up with a short advertisement of not even 1 minute. Francesco and I, under the ARIA project umbrella, we're organizing an online seminar on regularized ROMs. The timeline is very short, so it's this Thursday. Sorry about that. So we have here some visitors, and you can find more details at this, you know, on this webpage. So once again, Francesco was the main organizer, and hopefully, I mean, if you're interested, you're more than welcome to join us. And with this, I'll end my talk and wait for your questions, if any. Sorry for taking a bit longer than.
Thank you, Traian. So now the floor is open for additional questions on top of the ones that we already had throughout the talk. You can just unmute yourself, or if for any reason the mic doesn't work, you can write your question in the chat.
Don't be shy, really. I mean, you know, we've had some great questions. I would love to. I mean, there are many things I don't know. I'll be honest about, well, semi-honest. Yes, Masa.
Hi, Traian. I very much enjoyed your talk, and I'm particularly interested in this question of length scale, and I think it's very interesting. I want to ask a question. So I can see that, say we apply POD, the homogeneous isotropic turbulence data. In that case, I can see we can reduce the data to a kind of a single scale, right? But here you're looking at, I think if I got it correctly, you're looking at the channel flow. If we reduce it to a single length scale, do you think we might be potentially losing some essential information needed to actually stabilize the scheme?
Absolutely. So the answer is yes. And actually, so this is, I remember, so you asked something similar, and this is an excellent question. You're the first to ask this. I got this question again. That was Mike Graham from Wisconsin, asked similar stuff. So the question is whether defining one length scale for the turbulent channel flow is reasonable, and the answer is no. So just I want to be upfront. In fact, as Masa said, you see, so if you have isotropic turbulence, homogeneous isotropic, so think of turbulence in a cube, shape water in all directions, everything happens similarly in all directions. I think that this one length scale would do, as Masa said. But again, for turbulent channel flow, you have preferential direction, you have anisotropic structures. So if you have like a streak or like a tube, is one length scale enough to do everything? So no. And I think, so I don't know how to do it. I mean, I think that we need an anisotropic type of length scale. So like maybe 3 different length scales, for example, or like even maybe fancier stuff, aligned length scales. And in that case, probably you're right. So these, the Kolmogorov theory of turbulence might not even be true. So it's questionable using it to derive the length scale. But what I'm thinking for those cases is using particular cases. So in other words, if you look at turbulent channel flow, you look back, maybe you can use boundary layer type of theory and asymptotics. If you have flow past the cylinder, you have, maybe there is different types of asymptotics. And so maybe it's going to be problem dependent, the length scale, which is okay. I mean, but it's not going to be as beautiful and as general as this one. So you're right. This one does not do that. I don't really know how to do the extension, but my gut feeling is that using something problem dependent and boundary layer theory might get something a little bit better, let's say. But I don't know. The answer, you're right. The answer is I don't know. Good, excellent question.
So hello, Traian.
Hello.
It's Ramon Codina from Barcelona.
Oh, hi Ramon. How you doing?
How are you doing?
Not too bad.
Good
Not
to
too
see
bad.
you. Good to see you. And thank you very much for the presentation. It's been a pleasure to attend it. So, in fact, I have rather than a question, I have a comment. I don't know if I fully agree with you in something that you have said almost at the very beginning of the talk, which is that distinction between what is stabilization and what is closure. So, to me, the optimal situation would be one in which a closure gives you a stable scheme. So in a sense, if you're looking for something that has the effect of the terms that you neglect, this R plus 1 up to capital R, and that let's say, simulation of those terms already gives you a stable scheme, that to me would be the perfect situation. Don't you agree with that?
I completely agree. And this is, I mean, you called me on the right thing. So you're absolutely right. And so, in fact, that's the reason when I had to choose like one closure model, and I did choose the eddy viscosity type of closure models, because I think that they do exactly that. So you have, so physically speaking, what you expect from, Ramon, you said it perfectly. So you have these discarded modes. The role is to extract energy. And I think that you're absolutely right. The closure model should be stabilizing. So absolutely right. My comment was a little bit more shallow, and you're right. I mean, that distinction is maybe artificial, and there is a lot of overlapping between the two. I mean, one could argue that they're the same. But what I wanted to point out, really, my point was this: when I've been giving talks about closure for the past decade, and I've always had the feeling that, I mean, I'm not talking, I mean, you're like, I mean, you can teach this stuff, and you've done, but many times I had the feeling that people struggle understanding what exactly closure is and how you get it. And because I think that closure is trying to explain things from the root of the problem, which is the right way. I think these stabilizations are a little bit more easier to grasp, in the sense that you can think of those, I mean, the filter-based ones, that's what I'm talking about. You can think of those as, we have a problem and we know what the symptoms are. Well, let's try to alleviate the symptoms and see if this, actually this helps with our problem. So, but you're right. I mean, in the end, they're both stabilizing. Closure, eddy viscosity, and regularized ROMs. You're absolutely right. So they're both stabilizing. So yeah, probably at a fundamental level, they're doing the same thing. I agree with you. It's just that I feel that maybe when explaining, that's a personal opinion, when explain the filtered ROMs, the regularized ROMs, I think it's very easy it's easier to explain, in my opinion, than closure. It's just a matter of selling it, maybe not as much as like the fundamental. But I agree with you.
So it is true that the stabilization methods that you have talked about provide a simpler way to stabilization. This is obviously true. That is clear. But I just think that the optimal situation would be the one in which the closure already gives you the stabilization.
I agree. I agree.
I have another little comment
Yes.
that is something based on experience. You have talked about Galerkin, either Galerkin or Petrov-Galerkin, somehow implying that they work similarly. Our experience is that, that's why I'm asking. Our experience is that when you go to Navier-Stokes with highly nonlinear flows, Petrov-Galerkin is a must. So Galerkin, usually, in principle, the solution is the same in principle, but the truth is that the nonlinear behavior of Galerkin is very poor. And unless you resort to Petrov-Galerkin, you are unable to get a solution. What is your experience in that sense?
This is a great question. And this is, okay, my comment was tentative. So you're right. I mean, you called me on it, and this is fair. So my experience has been mostly with Galerkin ROMs, but I know that other groups, and so you and Charbel, and there are quite a few other groups that they've used Petrov-Galerkin, and classical CFD people, finite element, they like this method. I also like this method very much. So my feeling is, so I don't have a lot of experience with Petrov-Galerkin. I've looked at other groups, including yours, like who looked at that, and it works very well. And if I had to choose between Petrov-Galerkin and Galerkin, I would say that I would probably choose Petrov-Galerkin. But that being said, and this is tentative, this is my opinion, and I don't have anything to back it up at this point. I still believe that, so yes, Petrov-Galerkin works better than Galerkin, especially for the turbulent flows, as you said, yes. But I still think, and I'm curious to see what you think. So I still think that one could argue about improving even Petrov-Galerkin. So in other words, doing closure, for example, at the Petrov-Galerkin level.
Yes, no, that could, I mean, definitely Petrov-Galerkin could be improved, but my point is that it's just a matter of nonlinear behavior. So it's not about the quality of the solution or the stability of the solution. It's about the nonlinear behavior. So very often, if something does not converge using Galerkin, my advice is try Petrov-Galerkin. It will probably improve the nonlinear behavior. So it's just a matter of that. I mean, as soon as the nonlinearity is small or weak, then both work similarly. Okay.
Yeah. Yes, this is a good point. And then once again, Ramon, I mean, I'm honest. I don't have a lot of experience, but yes, I've seen that this is what you explained is what you described is the case. I would be interested to look more into this. I mean, so like if you but with the once again, my interest would be, can we improve even Petrov-Galerkin? If Petrov-Galerkin is working, then I mean, I don't know what closure and stabilization will do for that. But I would be interested to see if there is, and I think in my opinion, I've always thought that trying both would be something interesting. But yeah, I don't know. But I agree with you. And I just don't have enough experience to comment like about concrete that. So I don't know. That's the honest.
Thank you very much, and thank you again for the talk.
Sure, thank you, Ramon.
Okay, great. Are there further questions from the audience?
I have another question, if it's not too late.
Yes.
I'm wondering for the regularized ROM or filter ROM, I don't remember, when in the reducer model, the advecting velocity is filtered, but not
that's the Luray.
Yes,
that's the Luray ROM.
But the advected velocity is not filtered. So why what is the physical justification of choosing to filter this velocity and not that velocity?
Yeah, right. That's a Valentine. So that's a great question, and you should ask the creator of the method, Jean Luray. So one, I want to make clear. So this is my understanding. That's an excellent question. And I've asked myself the same question. And actually the answer is you can do it. And there are other people at the finite element level, this has been done, but that's a little bit more complicated. So as I said, this started with Jean Leray, was purely mathematical. He decided that that's exactly the regularity that you need to prove existence of solutions. And then he let the sequence, he chose the delta, he shrunk delta. And then he looked at the convergence of the solutions of the Leray Navier-Stokes, let's say. So why did he choose this one and not the other one? I guess that because he could prove the, well, I guess I can see in the energy estimate that that's more advantageous, right? But at the numerical level, you could do that, what you suggested. So why do, if in U dot grad U, why do you filter U, if I understood correctly, and not the grad U type of thing? And there are people who have looked into this at the finite element level. So there's the Navier-Stokes alpha people, like Foyash and Titi and all, and Daryl Holm, and they've looked at this. But my advisor in his group, so Bill Layton and there are others, they looked at filtering the grad U part. And there are pluses and minuses for each of them, I would say. But the most popular one is still the U bar dot grad U. So another thing, another important aspect is how easy is it to implement it. So there are differences. I don't remember the exact differences, but there are differences in how easy at the fundamental level, how easy is to implement one versus the other. So like one of them yields coupled systems, and that's a little bit, it increases the size of the system. So people don't like that. You double the size of the system, you don't like that. So that's another aspect to look into. But yeah, they've been considered at the finite element level. One could consider them at the ROM level. That's a good question.
Thank you.
You're welcome, Valentin. Great question.
Yeah. Other questions? Maybe Tommaso, I see that you have the mic open. No, sorry. Okay. So if that's not the case, then I think we can close here this first seminar. So we can thank Traian for his presentation, and all of you for attending and asking these questions and comments. The final few words from me are that you can look at our website that most probably all of you have received already, and in particular on this website there are the upcoming seminars, the links to register to the mailing list, and again most probably all of you have registered already, but in case some of your colleagues has forwarded this Zoom link to you, for the next time just make sure to register to the mailing list yourself, and we will send out the link directly to you. A further announcement is that in case you are not able to attend one of the seminars, but you are still interested in the topic, after a couple of days, we will upload the seminars to our YouTube channel, provided that the speaker agrees with that. So with that, the only two announcements I have left is to thank the project within which we are organizing this seminar, which is the ARIA project, as well as our 4 institutions, and on our website is you have the links to each of our institution, and to announce that next week at the same time we will have the second seminar in the series delivered by Tomás Chacón-Rebollo. So with that, I thank you for attending, and I hope to see you next week. Bye.
See ya.